Uh, Hi everybody, this is the continuation of Chapter 29, Magnetic Induction. I will start the lecture by giving a brief summary. The magnetic flux was defined by B dot A. As you will remember, this can be opened to be BA times cosine theta, where theta is the angle between the magnetic field and the area vector. So we have a loop like that, and this is the area vector, always perpendicular to the surface. And from this loop, if there is a magnetic field, okay, passing through this loop, there is a magnetic flux, and this magnetic flux induces some kind of current. And the direction of the current is such that the induced magnetic field will be totally opposite to this magnetic field if the magnetic field is increasing in time. Okay, so this was something that we had seen, so that some kind of current circulates this closed circuit. And if we want to get the magnetic flux in an arbitrary surface, then we have to really integrate small area like this. Suppose the loop is like that, and we take a small area vector, dA vector, and find out how the magnetic field passes from this surface, so that the angle between them is given as theta here. So this can be written as B cosine theta times dA. So this is the area integral, okay? So after you get this area integral, you get the magnetic flux. And Faraday's law states that the time rate of this magnetic flux induces some kind of potential difference. So this epsilon is the electromotive force, or just the voltage, or voltage difference. So basically, if we have these 2 points open and connected to a multimeter to measure the voltage across it, we will see that there is a voltage only when this magnetic flux changes in time. So how can we change the magnetic flux in time? As you see, the magnetic flux is given by the magnetic field, the area, and also the angle, cosine of the angle. So if we change any one of those, then the magnetic flux will be changing in time. So we have seen that Faraday's law induces some kind of current in the loop. And if there are n loops here, okay, then we multiply this by n. So basically, the electric field voltage is given by minus n d phi b over dt for n loops. Okay, so we had seen this earlier, and we had solved a few examples, and finally we came to the alternator. Okay, alternator. In the alternator, we just saw that if we have this kind of loop and the magnetic field direction is given like that, probably created from some kind of permanent magnet, okay? If we rotate the whole system in the clockwise direction, okay, and by using these rings, metal rings, and also the brushes, we can measure, okay, the voltage induced between these two wires, because this is connecting, okay, this whole thing just produces one loop. The reason that we have rings is that because of this rotation, we need a continuous contact between these two legs, and the only possible thing to have continuous contact without these cables twisting one on another is to have them touch in the interior surface of this ring. Probably has also some kind of depth like that, okay? So when you rotate this thing, you see that something changes. The magnetic field doesn't change because it's constant in time. But now the area vector changes. Suppose the area vector for this case was that, okay? If it is rotated, then the area vector rotates, and the angle between magnetic field and the area vector is going to be changing in time. So theta in this case is changing. So when theta changes, then the changing magnetic flux just produces electric field or potential. And we have seen that this potential was given by minus n d over dt, the flux. The flux was b times a times cosine theta, but theta was just omega t. If omega, which is the rotational frequency, was given, and don't forget, omega is always 2 pi f. It's not the frequency, but it's rotational frequency, and it is equal to frequency times 2 pi. Always remember that. So cosine omega t there. So now B and A are constants taken outside, and the electromotive force, or the potential difference, or as you see, the potential difference, doesn't matter. This is because this is epsilon. It doesn't mean that it's electric field. It's just the voltage induced between the 2 points of this current loop, which is in this case like a square, but not necessarily. It can also be round. Okay, but now n means that there are n number of windings. It means that when you go here for the first winding, you don't go here, but you continue wrapping this thing, and after n loops, you just come here, complete the whole circle. So that there will be n number of windings or loops. This is why we need n. So the number of voltage is increased by the number of loops. So if you want to get 2 volts, but you're getting 1 volt, then you have to double the number of rotations or the loops, basically. So this is given by minus NDA, because cosine omega t is the only time changing function. So if you take the derivative, you get the sine with sine omega t multiplying by w. So this becomes plus w sine the omega t. Okay, sine omega t. So from this we see that this electromotive force is time dependent, and the a omega sine omega t. So if the total resistance of this wire with n loops is R, then basically this current, the current which goes from this side and comes back to the other side, okay, the current can easily be found by just dividing this by the resistance, okay, because V equals epsilon equals IR, but the current is epsilon over R. So if you divide this by R, NBA divided by R, W times sine omega t. As you see, the current will be also a function of time. So this kind of functions, which are functions of time, okay, are called AC currents, alternating current, okay, alternating current. And if you look at how they change in time, it's like a sinusoidal, okay? Both I and epsilon will be sinusoidal. So where does this sign start? Of course, on the negative side also, it depends on the initial condition, where you start observing this potential, okay? So it may start from 0, it may start from maximum value, or any value in between. So this is the AC thing. But if you want to connect this to a multimeter, these AC voltages are measured such that RMS values are obtained. What does it mean? Because if you take the time average of sine omega t, it's just 0, because there are some plus and minus parts. If you take the average of this, you get 0, basically. But if you want to get something measurable, okay, related to peak voltage like that, you get the RMS of this value. Okay, what does it mean? RMS means that the RMS value of epsilon, which is average, which is like an average epsilon, is 1 over t, okay, integral sine square omega t dt. You take the square of this, okay, this RMS means root mean square, okay? So you get the square of the function, get the mean of it, it means that get the average of it, and then take the square root afterwards. So as you see, although sine omega t gives 0, and the average sine square omega t is a function like this, okay? So these negative parts are flipped to upper part, and probably the lengths are a little bit longer because you're squaring. So basically, as you see, all this, all these negative parts are flipped over, and then everything is positive. It means that when you take the average will not give you 0. So it will give you a certain value, and then if you divide it by t and take the square root, actually this is dividing the whole expression by 1 over square root of 2, okay? So, or just 2 over pi. Sometimes both of them are used, okay? So basically, then I RMS will be equal to just NBA W over R times 2 over pi, or just sometimes we just replace this by just 1 over square root of 2. So these two numbers are so close to each other. Basically, the RMS value will be having some kind of value which is multiplied by some constant, which comes from this kind of averaging technique. Okay, so we had seen this to do some calculations with some rotations and so on. Okay, now we will continue to slide wire generator. Slide wire generator. Okay, and this is the rail that we have here. Okay, so this is a long rail of wire. This is a conductive wire, and then on the top of this wire we put some kind of rod, not necessarily rectangular in shape. It can also be, the cross section can also be circular like that. So it doesn't matter, the shape doesn't matter, but this must be also metal, okay, or just conductive, okay. And then what we do is that we also apply a magnetic field downward. So if we show it sideways, it's much better. It's like that, okay? So now the magnetic fields that we apply to the system in this whole area, okay, the magnetic field is downward. So here the magnetic field is downward, okay? And also the area vectors are chosen downward because it's perpendicular to the surface, and this area vector and area vector are parallel to magnetic field. In this case, B dot A is just BA because they are in the same direction. So the area vector and the magnetic field vectors are going to be downward, okay, like that. Okay, so in this case, what we do is that we just pull this rod to right with some kind of velocity, and now we would like to examine what's happening here. Okay, we have to really understand what's going on. Really, very interesting things happen. As soon as we start this rod moving and coming to this position, for instance, the total area that, first of all, if there is a magnetic flux and this rod is stationary, nothing happens. And although there is a magnetic flux passing through the surface, because it doesn't change in time, nothing happens, and we don't observe anything, okay? We just don't see anything. But once you start to move this thing, as you see, the area increased. When the area is increased, it means that this is increasing in time, okay? So it means the flux increasing in time. So magnetic flux increases in time, okay? Why? Because the area increases in time. Because the rod is going to right, and the initial area was this, but now the area is almost doubled in the second case, okay? So now, in this case, we observe some kind of current circulating through this system. And we would like to find the direction of the current. And if we just look at how this thing behaves, as you see, the magnetic flux, the area increases in time. So this either magnetic field or the area or the angle increases, then the induced magnetic field will be always opposite to the original magnetic field direction. In order to have this magnetic field, which is in upper direction, you need a circulating current which is in the counterclockwise direction. So the current should flow like this. So all of a sudden, once you start moving, the current will flow, and then of course this current will continue from this rod. So the rod will also have current. So although the rod is moving, the current will be flowing from bottom to the upper part. So now if it is so, then we see that if the current is flowing, this part seems to be plus and this part seems to be minus, just like the power supply. So remember that the power supply always have leaving current from the positive terminal and incoming current to the negative terminal. So there will be some kind of potential difference between the two points, between this point and that point. Okay, so the current is flowing and also a potential difference is created. Of course, if the current moves on a conductor, the only way, suppose this is our conductor and the current flows. Why this current is able to flow? Because this potential at this point and there is a potential at this point, and they are not equal to each other. Besides, VA is greater than VB. Okay, in this case, the current is able to move from any conductor. We know this property. So if the current is moving from this, then there is a potential difference. But we will see that although the current may have a meaningful value, okay, this potential difference will be very small. Now let's just try to understand how we can analyze the situation. So let's draw it again on a bigger scale, okay, like that. Okay, so our rod is like this and moving this way, and the second time, okay, we see that it's right at this position. Now, if the velocity is v, and if this is delta x, okay, dx, then basically we can say that dx is equal to just v times delta t, okay, v times dt. Okay, so if it is so, then also we see that this area, if this side is given by L, suppose this is L, and the area of the whole thing, initial, suppose this area, and now the change in the area is this much, okay, this much. This is the change in the area, okay, dA. What is that? L times dx, because L is the, okay, is the parallel length, and dx is the perpendicular length, is just the product of them, gives you just dA. So having stated that dA is that, we can find that dA equals L times v dt, but if we divide it by time, dA over dt will be just equal to VL. Okay, so this is something that we will use later, and now we have to find out the direction of this change, and as I have explained earlier, this is positive because the area increases. If it is positive, then the change in the magnetic flux, then d phi b over dt, which is given by the magnetic field times dA over dt, okay? Because we don't have any cosine thing here, because the angle between the magnetic field and area is just 0. That's why cosine theta here, cosine theta is equal to 1. So it doesn't really count. So there is no cosine of any angle here. So the change in the magnetic flux is just that. And this is just VL, B, VL. So the change in the magnetic flux is simply B times V times L. And now if it is so, then the electromotive force or the potential difference between the two points, which is here, say this point and that point, since this is plus and minus epsilon, okay, let's remove this, epsilon is created, and this epsilon is given by minus BVL, okay, because of this minus sign. Remember that we add this minus sign. Of course, we have only one loop, okay, n is 1 in this case, okay. It's not easy to okay, continue this experiment with only one loop, because if you make this wire with more loops, but this will be with only one loop, and it's not going to make any difference. So that's why the number of loops in this case is just 1. Now we have seen this we have seen that you can measure some kind of potential difference if you just touch the tips of the multimeter to this upper point and the lower point. And we will see that this value is extremely small voltage or small potential difference. Okay, so now let's look at the force that is exerted on the wire, because if there is a loop and there is this wire, because of the current in the wire, some kind of force is exerted. Okay, and remember that it was given by that. So if there is a wire which is moving, okay, or now the wire is moving to the right, but the current is also passing through this wire. But if the current is passing through and there is an existence of the magnetic field, then there is a force on the wire. It's like that. Okay, so the wire is there and the current is passing here, and there is a magnetic field downward in our case. Okay, so now I has a direction this way and B has a direction, and as you see, they are perpendicular to each other. In this case, why is it so? Because here, the current is this way and magnetic field is that way, and there is 90 degrees, okay, between them. That's why this force on the rod will be to the right or to the left, is written as is F equals to I times LB, basically ILB. But what is the direction of this force? Okay, so we would like to find the direction of the force. I cross B, okay, is this way, as you see. I is that way and B is downward, so I cross B is that way. So the force direction will be this way. Okay, so this will be the force direction. So force is opposing to our pull. So basically, the force that we have now will be in this direction. So there will be some kind of force, okay, opposing our motion. Don't forget, this rod is still moving with some kind of velocity here. Because there is a force, it acts like a frictional force, because now it's against our motion direction, so that now this pulling business will not be so easy, okay? So you will have to spend some kind of power to do this, okay? So how do you find the power that you apply? How do you find that? So P is just F times this force times velocity, because if there is a force and also the thing is moving with V, then it means that if the force is opposing to our motion or just pulling direction, then this is the power that you have to exert, okay, on the system. So how can we find that? And we know that the current is just epsilon over R, okay, if the resistance of the total system is R. So what is R? R is the resistance between this part of the wire, this part of the wire, this part, and also the resistance of the rod. We know that any cable or any rod which has certain cross section, circular or just rectangular, doesn't matter, can create some kind of resistance. Suppose it is measured and the total resistance is R at a certain time, then of course this resistance changes, because now when you go from left to right, the lengths of these upper and lower wires are increasing, and R is slightly increasing if the whole system is moving from left to right. In this case, we can see that the current can be written as just B LV over R. Okay, the current is written like that. And since the force also is given by ILB, okay, then let's write the force, which is equal to ILB, but I is given by this expression, so that we have now B squared times L squared V divided by R. In this case, we multiply this by another V to get the power. We see that power is just B squared, okay, L squared, V squared over R. Now, look how we can analyze this result, okay? We see that the power becomes bigger if the magnetic field intensity is big. So if we apply a greater magnetic field downward, then the power that we have to apply should be bigger, okay, greater. Now, length, of course, length. If you double the length of this, then the amount of the power will be 4 times, because it's related to square of the length. And the velocity, how quick you are pulling to the right, is how much power you have to apply, okay? So also, of course, this power is related to the resistance, inversely related to the resistance. So if the resistance increases, then the power just reduces a little bit. So now, as you see, if the system is moving to the right, this is helping us, okay? Why? Because the resistance is slightly increasing due to the external extra parts of these wires, okay? So R is slightly increasing, so that the power that we have to apply is going to reduce just slightly if you are moving from left to right. This expression tells us that. So basically, this is just slide wire generator. So we just generated some kind of electric field between the 2 points. Why is there an electric field? Because this is plus and minus, and electric field will be in this direction. And obviously, the electric field is related to the potential difference, which is epsilon over L. Okay, so if electric field is asked in the exam, you can say that it is given by epsilon over L, because L is the length of this rod. As you see, now we gave a motion to this system, okay, and we applied a magnetic field, which is stationary magnetic field, and we produce some kind of voltage. So if you connect these two edges to a diode or small lamp, it will glow, because now you just create the mechanically you create some kind of electricity, just like you create electricity by rotating this alternator, okay? So now the only possible way of producing this kind of useful energy is the existence of the magnetic field. This is really the key issue. If there is no magnetic field, nothing happens, neither here nor there, okay? So now we are ready to continue, unless you have some questions. So you can go ahead and ask me questions if you have any. Okay. So this will be loaded to my YouTube page, okay? And if there is something you are missing, you can go ahead and just listen to that YouTube video. Okay, so now let's go on. Let's go on to magnetic induction. Don't forget magnetic induction. So we are now using the magnetic field and creating different kind of systems to create electricity or the current. Lenz's law is now what we will see. Okay, Lenz's law. Okay, so we would like to now connect the magnetic flux change to the electric field. And you know that just a few minutes ago, I said that the electric field times the length is just epsilon, okay? Or the electric field was epsilon over L, you remember that. So now, if we see that property, then we can really understand how we can go from the magnetic flux change to the electric field. And we get an expression for Faraday's law, including the electric field. Now, let's look at this loop system, okay? In this loop system here, okay, if the magnetic field is in upper direction, okay, not necessarily constant, and increasing in time, increasing in time. So it means that the magnetic flux is also increasing in time, because the area of this system is constant, and the angle between the area vector and magnetic field vectors, okay, vector are is just constant, not changing. In this case, the magnetic flux is changing, increasing in time, because the magnetic field is increasing in time. All the rest of the quantities for this magnetic flux, let's see, magnetic flux was given by B dot A, okay, which is equal to B A cosine theta. So the angle and the area constant, but the magnetic field is increasing in time. So basically, from this system, the everything is regular. Phi B is increasing in time. Then the induced magnetic field will be downward. But in order to create a downward magnetic field, you have to have the current this way. So circulating current will be, okay, in clockwise direction. So this is it. Okay, so the current will start from here and then arrive at point. In this case, this should be plus and this should be minus. If we assume that there is a power supply which is pushing the current from the positive terminal and accepting current to the negative terminal. Okay, this is how you can find out the polarity of this potential difference. We learned this earlier, okay? Now, we know that this is induced magnetic field, okay? Induced B field. Now, we already know how to get the direction of this induced magnetic field, but just let's write it systematically. Direction, okay? Direction of any B induction effect is such as to oppose the cause of the effect. In other words, the direction of the induced magnetic field is in opposite direction to the original magnetic field. If the magnetic flux is increasing in time. Actually, we have to add this. If phi B is increasing in time. If the magnetic field is reducing in time, everything is opposing. Okay, so how could we have magnetic field increasing or reducing? Very simple, because now you have to go look at the source, how the magnetic field is created. If the source is created by a permanent magnet, okay, then you can just move the permanent magnet closer to this loop or away from the loop. In this case, the magnetic flux line, the number of flux line will change, and the total magnetic field passing through the surface area will change in time. Of course, increasing means that you're just making this closer to this loop. Okay. In this case, the magnetic flux will increase. Okay, or you can just create this magnetic field by using an electromagnet, okay, like that. Suppose this electromagnet like this, okay. Let me draw a much better case like this, suppose, okay. And then you wind some kind of windings and apply some kind of current, okay. Now we do this experiment right in this region, okay. So now, because of this current, okay, the magnetic flux is like that through the system. The magnetic field lines will be passing through this and then go into the air and then jump from one side to another, okay. So the magnetic field lines will be this way. And we put our loop right in here, okay. So this is how we do the experiment. So the loop is right in there. Okay, so now how can we increase the magnetic flux? By just increasing this current, I0. Okay, if we increase this current, the magnetic field intensity will be increasing, passing through the system, whatever. So you can really design this experiment by any means. Okay, so now we would like to find out how to get that the whole magnetic flux change is related to the electric field. Okay, so let's look at this loop now. Remember that the loop was like that. So if we just take a little length of dl here, okay, the current is passing, circulating through here, and dl is this way in the direction of the current, and suppose that the whole system is moving with some kind of velocity, okay, with some kind of velocity like that. Suppose, okay, the whole rod is moving in this upper direction. Now we know that if there is a, of course, there is a magnetic field, okay, there is magnetic field still passing through the system. Without the existence of the magnetic field, really nothing is happening. So the force on the charge or this little segment is given by F equals Q V cross B. Okay, we know that. So the electric field then is equal to, so this is electric field F equals QE, remember? So the electric field then is given by V cross B. Okay, so the electric field is given by the V cross B. So now then the change in the electric field in this region, the epsilon is just this electric field, okay, times dl. But this electric field is V cross B, so that dE will be equal to V cross B dot dl. Okay, so in the case where the whole system is moving with some kind of velocity, then the change in the electric potential within this region is given by this expression. In this case, we can now add them up and get the total epsilon, which is equal to just the sum over the loop, okay, the total loop, V cross B, okay, dot dl. Okay, this is something that you can do. But don't forget, this V cross B is just the electric field. This is just electric field. Either you use this electric field directly here or V cross B, because the whole system is moving with some kind of velocity, probably getting away from the magnetic field or something. Then this will be equal to also E dot dl. Okay, E dot dl. Now we have stated that this electromotive force which is induced is nothing but equal to E dot dl. In this case, we can write this epsilon or just E dot dl, okay, dl, okay, this is the dot product, is going to be equal to minus d phi b over dt. So this is Faraday's law again, but written such that the electric field and the magnetic fields are just easily seen. So if you just discard this part, you see the relationship between the electric field and the magnetic field, because magnetic field is hidden inside here and electric field is there. So this equation tells me that if there is a magnetic field and magnetic flux and changing in time, it induces some kind of electric field. And if there is a circulation through some kind of length, then there is a voltage difference between these two tips. Okay, this is what this Faraday's law states. Okay, right? So basically, we will have some kind of electric and magnetic fields related to each other in this case. Now let's look what happens. If we look at the system, we would like to find the direction of the electric field, and if the current is flowing through this way, the electric field also will be, okay, like that. So electric field will be circulating electric field. Okay, at each point it will be tangent to this curve. So the electric field will be like circulating. Now what's happening is that, as you see, the magnetic field is this direction. If you look at this system, magnetic field will be in this direction, but the electric field will be circulating electric field. Okay, and the good thing is that they will be always perpendicular to each other. So at any point, okay, at any point, the electric field will be perpendicular. Okay, so now this is how the electric field is created. Now look at our system. If we have a regular circle, and if you look at from the top, and the magnetic field is given inside the page, let's say, B field is inside the page, okay? Now, if the flux is increasing in time, okay, if the magnetic flux is increasing in time downward, then the induced magnetic field will be in this upper direction, okay? So in this case, we will have the current circulating through this way, okay, to create induced magnetic field, okay? So the current will circulate like that. Don't forget the flux increases in time. So the magnetic field is downward, so the induced magnetic field will be upward. In order to create the upward direction of the induced magnetic field, the current should circulate like that. So if the current is circulating like this, it means that the electric fields also are going to be circulating electric fields. In other words, it's just a rotational electric field. So now, if you look at the system, okay, if there is a magnetic field this way, okay, the circulating electric field will be like that, okay? So electric field, just like this case, if the magnetic field is straight, electric field is circular. In this case, now let's look what we get. So if we have this electric field here, and then the length dl there, which is parallel to E, then E dot dl for our case, suppose the radius is r, E dot dl is nothing but equal to just E times 2 pi r, okay? Because they are parallel, the dot product goes away, and now we have this becomes E times the total dl, but the total dl is just 2 pi r, which happens to be the circumference of the whole radius, the whole circle. Okay, in this case, this is the left-hand side already obtained, but the right-hand side will be equal to, okay, just d minus d phi b over dt, okay, d phi b over dt. Now, if we look at this electric field from here, solve the electric field will be given by 1 over 2 pi r, okay, and d phi b over dt. So we can really get the magnitude or the direction of the electric field, but the magnitude is given by this expression. So now what will happen is that electric field, which is circulating electric field, will be reducing, okay, as 1 over r from this magnetic field. Okay, so from the center, okay, so if the radius gets bigger and bigger, the electric field becomes smaller and smaller because it is inversely related to the radius. Now, suppose that we have now this some kind of solenoid, okay? Suppose we have solenoid here, solenoid. How can we get the solenoid? We can have a cylindrical carton, for instance, or just cylindrical paper thing, and then just wind the wires around it, okay? And then we get solenoid. Now, if we pass some kind of current which is time changing, which is alternating current, it induces the magnetic field in this direction, okay? We know that the magnetic field in the solenoid will be in this direction because the current is going this way, okay? So the currents are going that way. Okay, the magnetic field will be towards right, but it will follow also how the current is changing in time. If the current is increasing in time, the magnetic field will also increase in time. So the amount of the magnetic field is given by just B, is given by just mu 0 n times I. Okay, n is the number density of these windings. So n happens to be just n over length, okay, n over length. So what number of turns is within some length L? So L is probably the length of the whole thing, okay? So the number density or the turn density or just loop density or winding density or something like that. So now if the magnetic field is given by this expression, okay, then the time rate of this is given by, you can really calculate the magnetic flux change by just multiplying the time rate of this by the area. So now the magnetic flux then will be equal to just mu 0 and I times area, okay? So d phi d over dt, which is this part, will be then equal to 1 over 2 pi r. So this will be equal to 2 pi times r times, okay, mu 0, mu 0, mu 0, okay, and a times dv over dt, or di over dt in this case. Okay, di over dt. As you see, the electric field is related to just some kind of constant, okay, which is related to the radius of this solenoid, okay. R is the radius of this solenoid, okay, and n is the number of windings divided per unit length, and the area is the cross section. And as you see, this coefficient is just a geometrical thing, and of course mu 0 is just the constant. So now the electric field is given by this expression. Now what we do is that if we divide this by length E over L, remember that electric field is volts per meter. So if we divide, okay, L, A, okay, then we can get the potential difference here instead of the electric field. Where is it? It's right here. It's N over L. Remember? N over L here. Small n is equal to capital N over L. So if you multiply L, the left-hand side is multiplied by L. This vanishes, and then we have the potential difference. So the potential difference will be equal to, if you use, of course, the minus sign, minus some kind of constant, and all this constant is going to be as L times di over dt, okay? So this is Lenz's law. So basically, some kind of constant. This constant is what? What is this constant? This constant is given as mu 0 and area divided by 2 pi r. Okay? So now what happens is that if the current is changing in time, this current of the solenoid is changing in time, a potential difference is created, okay? Created, and this is given by this expression. So this is really interesting. Okay. Any questions so far? Good. So we just go on. Okay. So now what happened? We have seen that if the magnetic field is this way, the electric field is that way, okay, rotational. And now remember that if there is a current passing through here, then the electric field will be in this direction, okay? But the magnetic field now will be in this direction. Now, what do these two cases show me? If the magnetic field is straight, electric field is circular. If the electric field is straight, then the magnetic field is circular. So why is it so? Why is it so? Because the electric field and magnetic field should be always perpendicular to each other. This is the property of the electromagnetic cases. So look at this electromagnetic wave. For the electromagnetic wave, which is the wave that we use in radio communication, or just laser waves, or the waves that we send to the universe, like to Mars or something, or maybe some device that we send to Mars, the communication waves are all electromagnetic waves, and they move, these waves, they move in the direction of k vector, which is the magnitude of that is 2 pi over lambda, which is the wave vector. So this is wave vector, okay, wave vector. So this is direction, it shows the direction of propagation. And now electric fields behave like that. So oscillating electric fields, okay. So oscillating electric fields will be like that. So plus and minus, okay. So basically the electric field lines will be oscillating like that. So these electric field lines. But now the magnetic field lines should always be there also along with these electric field lines, but they will be perpendicular to the electric field lines, these magnetic field lines. So they will be also circulating like that, okay? So now the magnetic fields will be like that. So going in the opposite direction. So the magnetic field lines now are in this direction, okay? And they are perpendicular to each other, as you see. At each point, they are perpendicular, okay? At each point, they are perpendicular to each other. Good. So this is just the electromagnetic wave moving in free space. So now if the electric field lines are remaining like that, okay, and of course the magnetic field lines should always be there. You cannot separate them from each other. So this is the wave vector or the propagation direction. And if this goes on, after some time, suppose the electric field vectors and the magnetic field vectors are again in the same direction, it means that the whole beam or the electromagnetic wave is plane polarized, okay? Plane polarized. So the polarized glasses that you have this kind of property. Only the electric field vector in some direction passes through the polarized glass, so that if you rotate the glass just a little bit, you don't see the vision, or just the amount of vision is reduced a little bit, so you can just get rid of some glares or some reflections, and then you have much nicer view, okay? Because all the reflections are eliminated. This is how the plane polarized glasses are made of. But now, if the electric field and the magnetic field lines together are rotating in time, suppose that after some time, electric field lines, this is electric field line and magnetic field line, okay? So suppose that electric field line rotated here and the magnetic field rotated that way, still, okay, still perpendicular to each other, of course. Now, this is going to be the rotational plane. So as you see, this is the whole system is rotating circularly. So this is circularly polarized wave. Circularly polarized. So the laser lights you have, okay? Usually, the laser light you have from the photodiode, you know, the things that are sold on the market, have the lasers almost circularly polarized. If you want to get a plane polarized laser light, for instance, or any light that is passing through the surface, you can use polarizers. So if you have circularly polarized wave, okay, like that, okay, circularly polarized, and if you use polarizer, okay, then you will have plane polarization. Okay, so why is it so? Because some molecules are stretched along this direction, so that only the electric fields in this direction passes through the other side of the polarizer, but all the others are just absorbed on the surface. So then from the circularly polarized wave, we can get the linear polarized thing. So this is the structure of the polarized glasses that you have. So they have these molecules stretch on the glass of this glass, okay? Good. So we learned how the magnetic field and electric fields are connected to each other. Now let's write Maxwell's equations. Maxwell's equations, okay? So the first one was E dot dA is equal to Q enclosed over epsilon zero, Gauss's law. You remember that, okay? So this Gauss's law, we solved several examples. And also another thing is that if this is the electric flux, okay, phi electric flux, we have magnetic flux, which is given as just B dot dA. If the magnetic flux is obtained through a closed surface, it is exactly equal to 0. So this is Gauss's law for the divergence. And now Faraday's law we just saw was this: E dot dl, okay, is equal to minus d phi d over dt, okay. So this is line integral, by the way. This is the area integral, but this is line integral. And another one was this: B dot dl, okay, B dot dl is equal to mu 0 I conductive, and then we add another term, which is another kind of displacement current, okay. This displacement current is such that it is equal to epsilon 0 times d phi e over dt. And now we would like to see how this displacement current is obtained, okay. If we look at this capacitor system, remember that we have like parallel plate capacitor, and then we apply some kind of current, the conduction current, okay, which is passing through this part and then leaving from the other side of the capacitor. So this is just the capacitor. Actually, in here there is no physical current, but it looks like the conduction current looks like moving to the right, as if it passes through this medium, but it doesn't. So this plate is covered by positive charges, and this plate is negative charges. We had seen this, okay? And the electric field will be this way. We had seen that electric field between the parallel plate capacitor is like that. Now, don't forget, Q equals just CV, okay? If the potential difference between the 2 points is V, then we have this case, but the capacitance for the parallel plate is just epsilon times A over D. Why do I write epsilon instead of epsilon 0? Maybe I can fill this region with some kind of dielectric constant, which is kappa times epsilon 0. This is the reason that I've written epsilon here times A. Now the potential difference is just AD, okay? If D is the distance of separation, okay? D is distance of separation. In this case, we see that if Q equals CV, okay, then we see that these cancel, and then we have electric field times area, but it's just electric flux. Q happens to be epsilon times phi E, electric flux, okay? So now, what happens is that this charge, this Q is like this, okay? But now the current is defined as dQ over dt, okay? So it is just epsilon times d phi E over dt. So as you see, this current is related to how the magnetic flux changes in this region, passing through these surfaces, okay? And you can define the current like that. This is some kind of displacement current. So we call this current as displacement current, okay? So now displacement current is written as, okay, displacement current is written as here. So this displacement current is given by that. So now this can be written as mu 0, the conduction current, plus, okay, epsilon times d phi E over dt. Okay? So if as you see in this Faraday's law, if the magnetic flux changes in time, it induces an electric field, but if the electric field changes in time, it induces a magnetic field. So there is a parallel connection, okay? So this structure of these equations are similar when magnetic field and electric field are reversed, except this constant, but this constant always can be put here because because it's constant, you can put here, okay? You can just include this with this expression so that it can be written as only simple right-hand side, just like the Faraday's law. So it means that the Maxwell's equations really are very important. But now the thing is that since this is so for the air, if this is epsilon 0, we have this term which is multiplying mu 0 epsilon 0. But if you look at the property of these constants, it is equal to 1 over c squared. Now, the coefficient of this will be mu 0 IC plus 1 over c squared times d phi E over dt, okay? So now, look how small we have this quantity, because c is 3 times 10 to the 10 meters per second. This is speed of light, and the square of that is just 9 times 10 to the 20, okay, c squared. But now 1 over 9 times 10 to the 20 is just 1 over 9, which is like 0.1 almost, times 10 to the minus 20 times this quantity. So this is so small. So basically displacement currents are extremely small, okay, than the conduction currents. But now the only place where this displacement current has an important value is when you have really very fast, high power lasers, you know, high power lasers. Because see, the electric field, see, d phi over dt is dE over dt inside, right? Because it is related to electric field times the area. So this is just d phi, okay, E over dt, okay? d phi E over dt is given by area times the electric field over dt. Now for some laser pulses, this delta t is in the order of femtosecond. So femtosecond is like in the order of 10 to the minus 15 seconds. So in this case, if you have a fraction of this femtosecond lasers, then if you just hit a surface, then a big amount of currents can be created because of these lasers, but not the regular lasers that we have. So it has to be very short laser, okay, like femtosecond lasers. In this case, displacement current can be should be included in the evaluation. But now look what's happening here. What's happening? So now, if there is a, if look at this system, if we say that what's happening with the with this area with radius r. So in this area with radius r, we have now, okay, the amount of conduction current, as if there is a conduction current passing through here, we are assuming this displacement current, okay? So we can assume that it's like a current, but passing through a fraction of the area. The total area is A, but pi r squared, okay, is just, the total radius is r, but the small radius is r. So that the area, radius r, so the current passing through this area, okay, passing will be equal to basically the conduction current times pi r squared divided by pi capital R squared. So this is small r, this is capital R, this is just a fraction. Now this is, so these pi's will cancel, and then this is the current that we are having. In this case, if you look at this case, look at here, so B dot dl, okay, B dot dl will be equal to B times 2 pi r, of course, and that will be equal to mu 0, current included, but just r square, I c times r square over capital R square. From this, we can find the magnetic field. The magnetic field is just mu 0 over 2 pi r over, okay, r square times IC. Wow, interesting, isn't it? Because all of a sudden we saw that in the capacitor there is a magnetic field, and also it's rotating magnetic field. So in this capacitor, the magnetic field is a rotating magnetic field like this, okay? So this is, now the magnetic field will be like the rotating magnetic field, although the electric field is perpendicular. So this electric field, magnetic field. So now all of a sudden we learn that actually inside the capacitors, not only electric field exists, but also there is a circulating magnetic field exists. So you have to be really careful with the calculation. So for those of you who are majoring in electronics, should realize that, okay, the capacitance always is under the effect of the magnetic field, and of course it means that it has some inductance also instead of capacitance, because we know that capacitors have capacitance, okay? They have capacitance, but they will also have some kind of inductance, okay? This inductance is important. So if you are using with these capacitors in high frequencies, at high frequencies, you have to be really also careful with the inductance effects, okay? So in here, if there is an electric field, of course, the magnetic field should accompany that. We have never told you earlier, but now we are telling, because we are now this Ampere's law, Faraday's law. Okay, now we are able to analyze the whole system. So life is not so easy, guys. Okay, so if you have this capacitance and you think that there is only electric field, you are wrong, because there is some kind of magnetic field due to the displacement current. Of course, the magnetic field intensity and the inductance is extremely small. Okay, so this really concludes this chapter, and it's the end of the whole lecture. So that now we are just closing the whole lecture, because this was the last chapter that we have seen. Okay, so this is the end of the lecture. Now I would like to thank you for listening to me.